Firstly, we're going to be looking at the atmosphere. Now, the atmosphere of the planet, Earth, was formed billions of years ago, at least 4 billion years ago. And in a way, we're lucky. We're lucky here on this planet because the Earth's gravity, the Earth is large enough for its gravity to be able to hold those gases to the surface. Because there are planets that are smaller than Earth where an atmosphere tried to form, but it literally leaked into space because there's not enough gravitational pull to hold it onto the surface. So we're a bit lucky in that regard. In fact, that's why we're here, I guess. But now, in the early days, of course, when the Earth was still forming, the atmosphere was nothing like what it is today. It was full of noxious gases. We wouldn't last 3 breaths because it was poisonous and very acidic. But as the Earth evolved, the gases that comprised the atmosphere slowly changed. And strangely enough, when life evolved, life itself had a big impact on the atmosphere. It was a two-way process. And finally, of course, the atmosphere ended up as it is today. And we all probably have heard that the modern atmosphere is around about 78% nitrogen and about 20% oxygen, which is the bit that we're interested in, and about 2% of other gases. Carbon dioxide, of course, is the big topical one that you hear about all the time, and many other gases, but a very small amount of it. Now, we are not interested in the chemistry of the atmosphere. And so from now on, it's interesting, by the way, that the bulk of the Earth's atmosphere is actually nitrogen, which is really an inert gas. Nitrogen doesn't like taking part in chemical reactions. When you breathe air in, you breathe in 80% nitrogen. And when you breathe out warm nitrogen. It didn't have any effect, it didn't do anything for you or to you. It's the oxygen that we're interested in when we breathe. And however, having said that, as I said, we're not that interested in the chemistry of the atmosphere. So we simply call it air. But it doesn't hurt to know that air is really a mixture of gases. It isn't a single gas at all. But the other thing is those percentages of concentration of the gases are fixed. You can go to the top of Mount Everest and the atmosphere will still be 78% nitrogen, 20% oxygen and 2% other gases. They're fixed all over the surface of the Earth at any height and at any place. Those gases remain in the same proportion, except for one. Except for one, that is the reason we're standing here talking, in fact, and that is water vapour. Water vapour is one of the gases under the heading of other, and it's present in the atmosphere, but importantly, it's present in very different proportions, and it varies greatly from place to place and from time to time. So water vapour is really what this course is all about. So we've got a lot to say about it. The rest of it we'll just call air. So from now on, we'll think of the atmosphere as air and water vapour. It's important to separate them because water vapour is the one that keeps changing as conditions change. So we've said all that. Now, the other thing that we need to talk about, because it's important, and we'll have to sort of introduce some of these words as we go, some of these terms, but if you don't understand them, you'll be mystified forever. If you did physics at school, well, then you're way ahead. But the fact is that the other thing we need to create weather is water vapour on one hand and heat. We have to have a form of energy to produce all of these phenomena that occur. And that energy is heat. That's the fuel that drives the weather. Heat is absolutely essential. And one of the things that's interesting is that we're going to look at now, how does heat change and how does heat behave across the surface of the Earth? Now, one interesting little sideline here. I don't blame them, but many years ago, the scientists were totally stumped by the idea of heat. They were trying to work out what the hell it is. What is the stuff you call heat? And not surprisingly, they imagined that it was like a fluid. They thought heat was like an invisible fluid. And they said, if I get a hot cannonball and I put it beside a cold cannonball, then eventually they reach the same temperature. And so that must be that the heat flows from one to the other. So it was natural they started thinking of heat as some sort of a substance. They thought it was an invisible fluid. And they actually thought you could weigh things. One theory was, if you weigh something when it's hot and then weigh it again when it's cold, it should be lighter because the heat's gone. Now, it's all right for us to laugh, but when they found it, they couldn't see the difference. They said, well, it's because our scales aren't good enough. We'll keep trying. But surely it must be true that if heat is a real thing, then why can't you weigh it? But now we know that's not the case. In fact, I guess it's true to say that we're still not sure what heat really is, but we do know how it behaves, and that's the key. I don't know what electricity is, but we know how electricity behaves, and that's all that matters. We can now use it to our advantage. So heat moves in 3 different ways, quite different. The first is called conduction, where 2 objects have to be in contact. Conduction requires physical contact. 2 objects have to touch each other. And if their temperature is different, then eventually their temperatures will reach the same level. And that's the process we call conduction. The thing to keep in the back of your head is conduction requires touch. You have to actually, when you put a saucepan on the hot plate of your stove, then it contacts the surface of the hot plate and the heat flows by touch, by conduction, from one hot thing to a cooler thing. And the next one, though, is more interesting. We're going to look at it in a lot more detail. Convection is a word we use, and it only applies to fluids. Convection can't occur in a solid. Convection is the everyday process of heat travelling in a fluid when the bottom layers become warm and lighter and they rise and move through the body of the fluid. And as those hot bubbles rise, then they carry heat with them. So that's heat's being transported by convection. Again, if I put a saucepan of water on the stove and I fill it with water, the first process is conduction. The bottom of the saucepan gets hot by contact. But then it also then conducts that heat to the lower layers of the water. But then that water, because it's hot, expands. And that expanded water is lighter, so it rises. And it carries the heat with it. Now that's a very specific process and it's different to conduction. It's created by actual currents that are generated and the fluid actually moves and forms currents that move within the body of the fluid. That's a unique and different method of heat transfer. Conduction and convection are 2 separate ideas, but convection is limited only to fluids. That means both gases and liquids. They're both fluids. That's another thing we often get wrong, We're very used to thinking of a fluid as a liquid. We imagine a fluid is only a liquid. But in physics, anything that flows is a fluid. So gases are fluids, and liquids are fluids. They're both fluids. Now, the last one, of course, is one that our poor little human brain is still trying to comprehend. It's called radiation. And it's sort of like magic, I guess, right? Because radiation can travel. It doesn't even need a medium. It doesn't need a liquid or a solid. Radiation can travel through a total vacuum. The light that's hitting the ground outside is radiation that left the sun about 8.5 minutes ago. And in those 8.5 minutes, it travelled the 93 million miles from the sun to us. And it got here, God knows how, right? It got here through empty space in the form of radiation. So it's a completely separate means of moving heat. The sun's heat actually does travel through space and heats the Earth, but it gets here by a process called radiation. In fact, for us on the surface of the Earth, as we'll see, the whole three processes work together in the atmosphere. And so we can't go on with MET unless we're going to use those words. And it'd be silly to use those words if you don't have any idea what they mean. So we're going to hear them every day from now on: conduction, convection, and radiation. So the sun's radiation carries heat to Earth through space. By the way, a lot of the atmosphere is transparent to radiation. The radiation passes through it as though it wasn't there, except for the gas called ozone, which we'll talk about shortly. The radiation passes straight through the atmosphere, but it hits the Earth's surface, the rocks and water down at the bottom of the Earth, of the atmosphere. And when it hits that surface, it then heats the surface. And then when it's heated the surface by conduction heats the lower layers of the atmosphere. And then because the lower layers of the atmosphere are getting hot, they expand, and you can think of them like bubbles in boiling water. They expand and they start to rise through the rest of the atmosphere. And so now convection takes place. So radiation is the prime mover. Radiation begins the process by arriving on Earth and heating the surface. And then conduction transfers that heat to the lower layers of the atmosphere, and then convection starts as bubbles of hot air rise through the atmosphere. So there's the planet Earth, and heat arrives by, now we give it a name, we call it solar radiation. Solar radiation hits the Earth on the daytime side. But at night, the Earth is now still warm. It received that heat from the sun. It's still warm. And at night, it's the Earth that's the hottest thing, because above the Earth is outer space where it's freezing cold. And so the Earth actually becomes the radiator at night. And the Earth sends out its heat in the form of what we call terrestrial radiation. So right now, this Earth's being heated by solar radiation coming in from the sun. But tonight, the Earth will lose that heat out to space by the process of terrestrial radiation. The interesting thing is, of course, and we don't want to get political here, but the argument has been going on for a long time: is the Earth getting hotter, or is it staying the same temperature, or is it getting colder? And it's all about these three things, right? If the amount of heat that comes into the Earth during the day is also retransmitted out to space during the night, then the Earth should stay at the same temperature. Imagine a bucket of water, and a tap is running into the bucket, and another tap is running at the bottom so the water can get out. If the water getting out is getting out at the same rate that it's coming in, then the level of water in the bucket stays constant. And that's what we're arguing. That's what all this argument is about. It's so gets so bitter at times in society now. Is the Earth getting hotter? There are two ways for the Earth to get hotter. Firstly, this can get stronger. The sun itself gets hotter, and so it sends more heat. So that would make the Earth hotter. But also the Earth would get hotter if we stopped the escape of heat, the terrestrial radiation. Okay? And some of the gases, and carbon dioxide is one, and water vapour is the other. Very powerful, strong, they call them greenhouse gases. Those gases tend to block the escape of heat. They don't increase the incoming heat. They hinder the escape. And so we turn off that tap on the bottom of the bucket, but we leave the top one pouring, and so that the level rises. And of course we haven't decided. Well, I better not, we don't want to get political, because some people say we have decided, but there's still argument, that's for sure. There's still argument whether the Earth is really getting hotter or colder, because we're talking here in fractions of degrees. And so, most of the heat is absorbed by the surface, goes back by conduction, and then convection starts. Now, another word that you'll hear is called advection. So convection occurs when hot bubbles of air rise through the atmosphere. That's called convection. Advection is the horizontal motion of air. And so if I wanted to make it as simple as possible, I could say it's wind. And that's not even incorrect. It's actually, that's not a exaggerated simplicity. Advection is wind. It's another word for wind. So if you want to impress your friends, you can say it's advecting. There's a strong advection today, all right? And they'll be impressed, because it's the same stuff. It's wind. And it's the horizontal transfer of air across the ground instead of the vertical movement. The vertical movement of air is convection, but advection is the horizontal movement. So these are all words that we want to be able to use, and I should feel happy that you'll know what I'm saying when we do talk about it. So that's advection, air travelling horizontally. Now there's a few other words we need to say, and these are important too. And I think it's worth spending a few minutes on this before we get into the nitty-gritty of it all. Latent heat is a term that is used a lot in general med, and it's really a little bit, we're going to talk more about it, by the way, later in more detail, but it's a little bit difficult to visualise, although there's plenty of evidence for what happens. Let me say this. Latent heat, latent means hidden, so latent heat means hidden heat. It means heat that doesn't actually cause a change of temperature. When latent heat is at work, we can't tell that it's happening because there's no change of temperature. So that's why they call it latent heat. Right, now let me say this. Imagine each of you, this is a good way, a little simple cartoon. Imagine each of you is a water molecule. Right, so I wave my magic wand and poof, you all are water molecules now. Right, now you can exist in three states. You can exist as a solid, a liquid, or a gas. Right now, so right now you are a solid because you're sitting in chairs and you can't move. When water molecules are in a fixed crystal and they haven't got any opportunity to travel or move, you'll always have your same neighbour, which you may or may not be happy about. Right? The water molecules, when water molecules can't travel anywhere, then we say they're solid. We say it's a solid state. But if we want to change that situation, we have to introduce heat. And this is what's called latent heat. Right? I would have to heat each one of you. Right? So if we carried on this little pantomime, we'd say you're all sitting in your chairs now, you're a solid. Now if we increase the energy by increasing the heat, and so you all get up and you start walking around the room, bumping into each other in the walls. I better blindfold you as well, right? Molecules can't see. And so you're bumping into each other, you're bumping into the rooms. You have now changed your state. You're no longer fixed, you're now mobile. And therefore, you are now a liquid. And there's no part of the room that you can't travel into. You'll flow wherever there's space. But you'll stay on the floor, you're a liquid. Now, if we crank up the energy, and this is a hard one to demonstrate, right? Then you all turn into Superman, and you take off, and you start flying around the room, banging into each other and the walls and the roof, and you become a gas. You're the same water molecules, but it depends on how you're organised as to what we call you. We call you a solid when you're all fixed in space, in one place. We call you a fluid when you're free to move in one plane horizontally. And we call you a gas when you can fill the whole space that you're in. And then, of course, you can go backwards now. While you're all busily flying around the room, I can turn the energy down and you all fall onto the floor. Now you've turned back into a liquid. And then you all get up and go back into your seats, and now you're a solid again. That's exactly what the molecules are doing. But it requires heat to do that. To go up to a more energetic state, I have to bring heat in. The latent heat has to come in to give you that energy to make you get off your chairs. But if you go back the other way, then you've got to dump that heat. You've got to get rid of it and push it out. So latent heat is necessary to make a liquid like water change its state. And whenever you go up the energy ladder, then you have to suck heat in. If you go down the energy ladder, then you have to push heat out of the system. That's going to become an important concept in the next few hours as we talk. And so, when a cloud forms, you know, if you ask a lot of people what a cloud is, they'll say it's water vapour. And most people don't blink an eyelid. They say, oh yeah, cloud's water vapour. No, it's not. Water vapour is invisible. It's an invisible gas. It's in this room right now. We can't see it. If a cloud was made of water vapour, then it would not be visible. Right? But what's happening in a cloud is that the water vapour in the atmosphere is turning back into liquid water droplets. And so those little molecules can no longer fly all over the place. They're all staying within that bubble of that sphere of liquid. And they're trapped in there now, but they're in the form of a liquid. That's what reflects the light, and that's what makes the cloud visible to us. That means when I'm looking at a cloud, I'm actually looking at liquid water. Droplets of liquid water, not vapour, it's liquid water. And therefore when a cloud forms, when a cumulus cloud like that forms, then it has to dump heat. It has to go down the energy ladder from gas to liquid. And that means clouds naturally warm the surroundings. A cumulus cloud, when you get your instrument rating, if you're flying a non-pressurised aeroplane with no air conditioning, if you fly into a cumulus cloud, you'll feel that it's warmer inside the cloud than out. It's a bit like stepping out of your car when you've had the air conditioning on, and inside the cloud is warmer than outside, because the cloud is dumping its heat out into the air, so that the water droplets can form. Those water droplets can't form unless they get rid of their energy. They get rid of their heat, latent heat. And so a cloud is actually condensation. The condensation is the process of turning from gas to liquid, and the environment has to accept the extra heat. That heat is pushed into the air surrounding the cloud, or more correctly, it's pushed into the air within the cloud, between the little particles of liquid. So whenever you see a cloud forming, you're looking at the process of condensation coming down the ladder from vapour to liquid. Now the opposite happens. If water evaporates, then it has the opposite effect. It has to get heat to evaporate. And so it'll take that heat, if it's forced to evaporate, it'll take that heat out of the surroundings. And that's why wet t-shirt competitions work. Because if you put on a wet t-shirt and stand in the wind, then you're forcing the water to evaporate. It needs heat. It takes the heat out of you. It cools you down. There's an example there. Put your cameras away, come on. Right. So, that's evaporation. That's evaporation. In the cloud, we have the process of condensation, heating the surroundings. When the opposite occurs, when the liquid turns back into a vapour, then the environment is cooled by the process of evaporation. You know, one of the most interesting little pieces of invention ever was the thing they called a water bag, which you don't see much of, but if you come from out west you'll know. Right? A water bag looked a bit like a briefcase, like that. And it had a little spout at that end, there. And it's made out of canvas, so that canvas is not quite waterproof. So when you put water in a water bag, it slowly seeps through the canvas, and the outside of the bag is always damp. Same process when you sweat. That's what your body does, same thing as a water bag. It pushes water out into your skin so it can evaporate. And that evaporation will cool you. So these water bags work very well out west where the air is dry and there's a lot of evaporation. And some people tie them on the bull bar of their truck so that as they drive, the wind blows on them all the time. And that water in that bag will get to a very pleasant, cool temperature and make a lovely cool drink without any refrigeration or anything else, just purely by evaporation. The evaporation of the water, it sucks the heat out of its environment to allow it to evaporate. So the other one is another interesting term, and you'll hear it too. It's called specific heat. Now, it's also easy to understand. The good thing about this is most of this you already know. We're just putting out words that words that are used that you may not have heard before. When we talk about specific heat, we are simply saying that some substances get hot easily, and some substances are hard to heat. It works both ways. There are some materials that are easy to heat, but the materials that are easy to heat are also easy to cool. Specific heat means a material with a low specific heat is something that will easily heat up, but when you take the heat away, it'll easily cool down. Whereas a material with a high specific heat is very hard to make it hot. But once you have made it hot, it's very hard to cool it down. And so Here's an example. Water, lucky for us really, water has got a very high specific heat. In fact, water has the highest specific heat of any substance, of any natural substance that isn't manufactured by man. Any naturally occurring substance, water has got the highest specific heat of all of them. It's very hard to make water hot. It takes a lot of energy to make water hot. If ever you look at the electric light meter in your house, when your hot water system cuts in, you'll see that when the hot water system cuts in, all of a sudden the light meter goes around and around. It's chewing up power like mad. It's very hard to heat water. But once it gets hot, then it's hard to cool it down again. We can put hot water in a bottle, in a rubber bottle, and use it as a hot water bottle, and it'll stay warm for a long time. It'll take a long time to cool. A long time to heat it, but a long time to cool it. Whereas things with a low specific heat are the opposite. They get hot like mad very quickly, but as soon as you take the heat source away, they cool down straight away. And so a good example of that would be beach sand. We've all had the experience on a hot summer's day with no cloud, so that the sun's radiation can hit the sand directly, and by mid-afternoon you're flat out walking across the sand in your bare feet because it actually burns, it's hot. And you watch people, you would have seen this happen, when you have to walk across hot sand, you run from shade to shade. Wherever there's a shaded spot, because that part doesn't get hot. The sand gets hot very quickly, but take away the sunshine and the sand gets cold very quickly. So if I was running across this beach, I'd be running for the shade of the tree. Because that sand it's been there all morning, but the sun hasn't shone on it. And so it's had hardly any effect. Whereas this sand is extremely hot. It has a low specific heat. High specific heat means it's hard to make it hot. A low specific heat means it's easy to make it hot. That's just 10 little things. Now, the next thing I want to talk about is another important idea to understand general met. As scientists became interested in the atmosphere, by the way, they became very interested in the atmosphere long before there were aeroplanes. One of the things that brought it home was when they invented hot air balloons. The French were really keen on that. There was a sort of instead of going to the footy on Saturday afternoon, you went down to the park and watched some galah disappear into the sky in a hot air balloon. But some of them died. And so they were interested in what's going on. They had no idea how hostile the atmosphere becomes when you go high enough. They didn't realise how very cold it quickly gets and how rapidly the pressure drops to the point where you can't breathe. And they did lovely considerate things like sending up chooks and cats and things, and finding out when they came back down they were dead. So we started, and we still do it. This is the interesting point. We explore the atmosphere by sending up thermometers, and they transmit by radio the temperature and the height. They have their own altimeter and their own thermometer. So they know their height and they know the temperature. So they can send back to Earth the temperature at any height throughout the atmosphere. And we can draw a graph of that. And so we have a gadget called a radiosonde, and this is one that's been used, the radiosonde, and put out by Philips. And it contains, well, the remains of an altimeter. You see a little capsule in there, a little metal capsule, an altimeter and a thermometer and a radio transmitter. And it's attached to a helium balloon. And so they send these up Hundreds are sent up every day. People don't even realise it. They're sent up to constantly see what's going on with temperature in the atmosphere. And we'll see soon that that's really important because it describes why you have a day like yesterday. The stability of the atmosphere. Are you going to have a clear blue sky, or are you going to have pouring rain? It all depends on one thing: what's going on with the temperature in the atmosphere. It's vital information they need. And so these things are sent up, and if you went down to Brisbane Airport, they're nearly always from airports, and that's about the safest way to do it, because then they know where it is, and pretty soon it's going to be higher than's likely to cause a problem with aircraft. So it actually, eventually, by the way, the balloon, the helium balloon that carries it will keep expanding as it goes higher into lower pressure, and the balloon will rupture, and then it'll fall. And it falls on a little parachute, and it's made of this nice soft stuff. So if you're standing at your barbecue one day and it falls on you, then you can just say to your friends, "Be calm, it's just a radiosonde." Right? So, strangely enough, they're hardly ever found. It just goes to show how much of the Earth doesn't have people. We live amongst all these people all the time. We see people. But over the whole planet, there's a lot of places where there ain't no people. And so these things very often are never ever seen again. They have a sign in here. They have a little note on them here. And it says, roughly translated, "If you find this, you can have it." Right? Because people used to find them and go and think, "Oh, it fell off the space shuttle," probably worth millions of dollars. And so they hop in their horse and gallop in to Melbourne and hand it back and say, "Look what I found." And the guy says, "Oh yeah, that's the radiosonde, you can have it if you like. But we don't want it anymore. It's only good for one shot." But that'd be a good business for Philips. Right? You build all these things and it can only be used once, and that's the end of it. And hundreds every day go up. So it's an amazing thing. So here it is. Imagine we send up a radiosonde and it transmits back to Earth both its height and the current temperature at that height. And so it goes up into the sky, and we record the temperature that's being sent back. Now, quite obviously, it gets colder as I go up, because the heat from the sun has heated the ground first, and then the ground has transmitted that heat to the air. So the heat has to work its way from the ground up, not from up top down. When I was a kid, I used to get worried about that. And I used to say, "Well, how come it gets cold when you go up? Aren't you getting closer to the sun?" But we have to understand how radiation works. Radiation goes straight through the air and heats the ground, and then the heat comes back again from the ground. And so naturally, this graph leans to the left. So as height increases, temperature decreases. And we send it up and we plot that temperature. Now, high in the atmosphere, there is a concentration of a certain gas called ozone. And it's got all sorts of interesting properties, but the one that interests us at the moment is that ozone has an amazing ability to absorb the sun's radiation. It's just as well, because without it, we wouldn't exist, at least in our present form. We'd probably look like cockroaches or something, so that we could suffer strong radiation without getting cancers and all sorts of things. The ozone acts as an umbrella for us creatures who live on the surface of the Earth. Ozone is a triatomic form of oxygen. So normal oxygen is O2, ozone is O3. Normal oxygen gets around in pairs, atoms joined up together. Ozone gets around in threes. And like most threesomes, it's unstable. And it doesn't last long before there's a split. Right? So ozone has to be completely replaced, continuously replaced. One of the main things that replaces it is lightning strikes. Lightning tends to shock some of the oxygen to get into threes and form ozone. And as that ozone, it tends to concentrate at one level, way up higher than aeroplanes ever fly, about 150,000 feet. There's a layer across the whole Earth of ozone. And as I said, lucky for us that it exists. And a few years ago they discovered a big hole in the ozone layer. Luckily it was over Antarctica. And they found out why it was being caused, because of certain gases that are used in refrigeration, fluorocarbons. And they banned them. Worldwide they banned them and made refrigerators use different gas. And that was a great success story because it worked. The ozone hole has now nearly repaired itself. And so if we removed the ozone, we'd all be in dire straits. But it's way up there, way up high, and it absorbs. Now, if it absorbs all that radiation, it must get hot, and it does. It's actually quite warm. This is where the usualizer that we've been used to talking about, this is where it suddenly breaks down, because the temperature no longer drops at 2 degrees. If that balloon keeps going, after a certain height, as it approaches the ozone layer, then the initial thing that happens is it's trying to cool, but it's getting closer to the ozone layer, which is trying to heat it. And so for a little while, those two effects balance, what they call thermal equilibrium. And so for a little while, the temperature stays the same with height. It goes vertical like that. And then as you get closer to the ozone layer, the temperature actually increases with height. It's a complete opposite of what we're used to thinking down at the levels that we fly at. Now, if you were a scientist and you wanted to study the atmosphere, one of the first things a scientist does is classify. If I want to study butterflies, then I break the butterflies up into groups that have something in common. And then I sort of collect them and put them into a category. And so when we look at the atmosphere, we try to break the atmosphere up into zones where something happens that's common to that layer. Now, if I asked you then to identify, where would you draw the first line to say this is a certain layer in the atmosphere? Well, surely the temperature has been dropping with height, and then it suddenly stops dropping. So that seems to me like a good place to draw a line and say this is going to be a layer of the atmosphere where temperature drops with height. Right. And so we do that. We draw a layer, we draw a line through, and we call it the troposphere. The troposphere is the layer in the atmosphere where if you go up, you'll encounter colder air. At least in ISA. Right? As I go up, the temperature can be expected to drop until I hit the top of the troposphere. And that is the layer where colder air is found above warmer air. I should have said, Yeah, no, that's correct. Colder air is found above warmer. As you go up, it gets colder. Now, if I asked you to find another place where you might draw a line, you'd be tempted to say this point where the temperature has been constant and then it starts to increase. In fact, the scientists don't bother with that one. All they're interested in is does it actually not drop? Does the temperature not drop with height? So the two layers we're talking about are the bottom layer, the tropopause, the troposphere. The troposphere is the layer where temperature does drop with height. And the next layer up, the stratosphere, is the layer where temperature does not drop. It doesn't matter that it stays constant. It either drops or it doesn't drop. If temperature doesn't drop with height, we're talking about the stratosphere. And then we also give a name to the dividing line between them. So we have the troposphere and then the stratosphere. And we might as well forget it after that because we're not ever going to fly any higher than that. The layer between them is called the tropopause. I suppose that's a good name. Pause means a stop or a change. And so the temperature has been dropping with height and then it stops. And it stops dropping. And so that line, that level, is called the tropopause. Notice the tropopause is not a layer. It's the name we give to the dividing line between the layers. If I asked you to name the layer above the troposphere, then you'd say it's the stratosphere. The layer above it is the stratosphere. The tropopause is simply the line that divides them. It's, if you like, it's the roof of the tropopause. It's just like a roof. By the way, it keeps going as you get higher, but as pilots, we're not that interested unless you own a pacer, because you're not going to end up at those sort of heights. And so that's the tropopause. Stratosphere, troposphere, tropopause, stratosphere, and there is such a thing as the stratopause. And then there's other layers above that, but we might be just out of curiosity name them, but they're not of any interest to us. So the tropopause is really quite a thin layer, by the way, compared to the whole Earth. And it averages about 36,000 feet. The tropopause is about 36,000 feet average, but it changes quite a lot, right? It's something like 60,000 feet over the equator, and it's about 30,000 feet over the poles. It's about half as high over the poles. But over a country like Australia, throughout the whole geography of Australia, the tropopause is about 36,000. Now, as you can imagine, the atmosphere is not a predictable thing. And so it isn't exactly 36,000. It's sometimes, some days it's higher, some days it's lower. That's why we do this. That's why we send this up, because we don't know where it is. But in ISA, it's 36,000 feet. Right? But on any one day, it may not be at that particular height. So when a jumbo jet is flying in cruise on an international flight, he's often at that height, or 39,000 sometimes. They're usually high in the high 30s. So they're flying pretty much at the tropopause. And so now this has another important consequence, because remember we said that convection in a gas or a liquid, relies on a hot spot, some hot spot on the ground, transfers its heat to the air, and that air becomes hot by conduction, and then because it's hot air it expands and becomes lighter. It's common knowledge surely that hot air is lighter. Everybody knows that. That's why hot air balloons work. That's why hot air goes up the chimney and not down. It goes up because it's light. And so that means the process of convection begins. But now that we've had this talk, let's have a look at it. Convection is this hot air is rising. Why is the hot air rising? It's rising because it's hotter than the surrounding air. It's hot air going into colder environments. And so it'll rise. That hot air will rise while ever it's hotter than the surroundings. So it goes quite happily up to the tropopause. But when that hot air tries to cross that line and go up into the stratosphere, then it quickly encounters air that is either equal to its temperature or hotter than it. Now, if the surrounding air is hotter than the rising air has no reason to rise. Its buoyancy, as we say, its buoyancy is the fact that it's floating and rising. It depends only on the fact that its temperature is different. So if the temperature is different, if the temperature of the surrounding air gets warmer, then that'll put the brakes on that rising air and it'll suddenly stop. So the end result is that convection in the Earth's atmosphere, convection is pretty much limited to the troposphere. And therefore nearly all the clouds and nearly all of the meteorological phenomenon that we see on the ground is limited to the troposphere. And in fact, for the rest of this course, we'll be mainly interested in what goes on in the troposphere. Not above it, because air can never rise past the tropopause. Well, in fact it can, but it will at least begin to stop rising as soon as it crosses the tropopause. Now here's a little, don't take this too seriously, but I did hear that somebody said they'd had a question in Met that asked them about some of the upper layers. And so here's the planet Earth, and that dark colour, the dark shading here, represents the troposphere. Okay, so that's the troposphere, and notice that it's drawn so that it's deeper over the equator than over the poles. About twice as high over the equator. And then you have the tropopause, which is the dividing line. And then above that we have the stratosphere and the stratopause. But above that still we have other layers with other attributes that are common. And that's called the mesosphere, the one above the stratosphere, the mesosphere and the mesopause. Right? And then we go above that and we get the thermosphere and the thermopause. And then above that there's the exosphere and the exopause. By the way, the atmosphere, of course, doesn't suddenly stop. It actually just keeps getting thinner and thinner. Even the International Space Station is actually in the atmosphere. And that's why they have to keep refueling it and nudging it back into orbit, because it's over a few months it slowly starts to slow down with drag. Of course, it's tiny bit of drag, but it finally has its way. It finally affects it. If you abandon the International Space Station today, then this time next year it would be gone. It actually has to be kept in there. Most of the time it doesn't need engines, but every now and then they have to boost it because it slowly drops out of orbit. So even that is in the atmosphere in that sense. The atmosphere it's not like putting your head out of a swimming pool. Right? I don't sort of like put my head out of the pool and there's the water and there's the air. The atmosphere just gets slowly thinner and thinner and thinner and thinner it's hard to find an end. But we can find these changes in layers within the atmosphere. Somebody said they saw a question where you had to say I nearly said menopause. I mean, menosphere, right? Mesosphere, it's called. And so let's zero back into reality, and we'll talk about the one that we're going to get familiar with, the troposphere and the tropopause. That's where our discussion will spend most of its time. Over the equator, about 60,000 feet. Over the poles, about 30,000. And a reasonable guess over the continent of Australia, somewhere in the high 30s. In Isa, 36,000. There's a photo of it, by the way. Here's an interesting point. That's actually taken from the International Space Station, and the sun is at just the right angle. They're on the nighttime side of the Earth, coming around into sunrise. And that, because of all the dust and smoke, because convection doesn't go any higher than the tropopause, then all the dust and smoke in the atmosphere, it's all trapped in there. And it stays like that. And so it reflects sunlight. And from space we can see it as a sort of dirty layer of a hazy looking layer. That's all the stuff that's trapped. But look how thin it is. It's quite surprising. In fact, you know, some scientists once worked out that if you want to know how thick the tropopause is, then cut an apple in half and look at the half of the apple. The skin of the apple is roughly the same proportion as the depth of the troposphere. Yeah. And then people, you know, now I will get political, because people say, well, you know, hundreds of thousands of jets flying all day and all night all over the world, pumping out carbon dioxide into the atmosphere in their exhaust, and that never ends at roughly 11 tonnes an hour. And those surely it isn't just going away. It's all staying there because of that limit, because of that because of the action of the tropopause. Anything that's dumped into the air can't get out. It'll stay there. It'll just keep circulating. And so, of course, it's got to have some effect. It's like people are just beginning to realise now that you can throw whatever you like in the ocean and it sinks and disappears. It's gone. Well, that was a good idea for a while. And now we're realising, hang on, the ocean isn't infinite. There is a limit to how much you can put into it before it starts to come back to you. And so the troposphere at 36,000 feet, 6,000 feet is a nautical mile, the troposphere is about 6 miles deep. The diameter of the Earth is about 8,000 miles. So the troposphere compared to the Earth is like comparing 6 with 8,000. It's a tiny little thin thing. It's not a very, very big, very deep layer. So, therefore, around the Earth, we have that happening. Now, of course, because of the shape of the Earth, as the sun's rays arrive from outer space, they don't heat the Earth evenly. The Earth isn't a flat wall, it's a curve. And so as the sun's rays arrive, they hit the region near the equator. It gets a lot hotter than the poles. You learnt that in grade 3 at primary school anyway, right? The equator gets hotter simply because the equator is copying the sun rays at right angles, whereas the poles are copying the sun's rays at a shallow angle. The sun is always almost on the horizon, at the poles. It never gets up. It just stays close to the horizon. But at the equator, it actually gets to the point where it's vertical. And that means this gets hotter. Now, there's another important thing I'll say. Maybe you've never thought of it before, but if you have a look at the Earth and a globe, you'll see that almost all the land on the planet is in the northern hemisphere. Almost all of the land is in the northern hemisphere. There's hardly any land in the southern hemisphere. And now, we said earlier, water has a high specific heat. Water is hard to heat and it's hard to cool. So the temperatures in the southern hemisphere tend to be relatively stable throughout the seasons. Our winter, today it's pleasantly cool, but you wouldn't say it's freezing cold. I don't see too many people with jumpers on, right? So our winter is not a super cold, and our summers are hot, yeah, but they're not super hot. Go to the northern hemisphere, and for the same latitude, the temperature at any given latitude in winter is far colder than summer, and summer is far hotter. The temperatures change much more dramatically. You know, for example, you have a look at, well, here's Florida, right? Or mate, let's make it New York, right? There's New York on the globe. That's the latitude. Now, if I keep that latitude and put it in the southern hemisphere, like this, all right, same, I didn't move it. Huh? It's about Sydney. New York is roughly close to Sydney's latitude. In wintertime, you're up to your bum in snow in New York in some years, and the traffic can't move. And in summer, they're taking people to hospital because of the heat. We don't get that here because we're in the southern hemisphere, and the oceans have a huge effect. They stabilise the temperatures. Temperatures at latitude for latitude, it'll be far hotter and colder at any given latitude because of the land masses. All the land masses, or not all, but a very big percentage of the land masses is in the northern hemisphere. And that means that at the equator gets hotter because the sun's hitting it at right angles. So the air on the ground gets hotter and it rises, but it only rises to the tropopause. So now we can start making some benefit from having that talk. The air on the ground, the air at the surface rises because of the heat, but only to the tropopause. And then more hot air is coming up underneath it. And so when it gets to the tropopause, it starts to spread horizontally. And therefore it's now way up high and it starts to cool. And as it cools, it gets more dense and it eventually sinks again. We'll limit our discussion to the southern hemisphere. I can promise your exam will stay in the southern hemisphere. And so this air got hot and it rose and started heading south at very high altitudes. And then it finally sunk, finally got cold enough to sink, and it came down to the surface, and then it gets dragged back because of this low pressure. It gets dragged back, and so the cycle keeps going. And so a circulating cell is formed in the atmosphere. And we call it the tropical cell. The tropical cell is a distinct circulation in the Earth's atmosphere. Air is constantly rising over the equator. By the way, here's another point we often don't think of. If I run my finger around the equator, I see that it's nearly all water. I go across here, across the Pacific, and then I go across this little bit of South America, and then I go across the Atlantic, and then this fairly thin part of Africa, and then I go across here where there's really only islands, still mostly water. So nearly all the equator is water, and it's also hot. It's hot water, so it's got lots of water vapour, and the air is constantly rising. So as the rising air carries that water vapour with it, and as it goes up and cools, that water vapour condenses into cloud. And then eventually that cloud will become so thick and dense that it'll cause rain to fall. So all around the equator, this area, there are low pressure regions because of the rising air, but they're low pressure regions with a really high amount of cloud. And so it's almost always raining. Right? It's nearly always raining in that region. And I think I read somewhere that the post office in Lae in New Guinea had a record where it has rained every day since the record started. Not all day, but there's been some rain virtually every day. And because that area of the earth is both hot and wet. And so when there is land, the land is jungle, right? Notice it's no secret that the Amazon, in this very region where the equator crosses, is the Amazon jungle and the Amazon River. And this region is the thick jungle, the Congo in Africa, and more jungle and more wet tropics, right? And of course all of the islands above us, same deal. They get more than their share of heat and rain. Now what else happens? Let's look at this. Down at the poles, we have cold air that's sinking. And when that cold air sinks, it hits the ground, it's got to go somewhere, so it spreads. And more cold air sinks behind it, and so that air starts to head north. And finally, below Australia, by the way, below the Australian, below Tasmania, it doesn't even make it to Tasmania, and then it warms as it goes because it's still cold, but it's warming. And so finally it gets warm enough to rise, and it forms another cell called the polar cell. Now because this cell is rotating clockwise from where you sit, that cell is rotating like that, and this cell is rotating like that, then the air in between them, because air has got a property called viscosity, air is sticky stuff, and so these rotating cells form a third cell that rotates in sympathy with them. And so then we have the mid-latitude cell, where it rotates like the whole three rotate like cogwheels. So this one rotates, and it drags this one with it. And then this one rotates, and so this one rotates in sympathy with the other two. And so the Earth, the hemisphere that we live in, has three big, gigantic cells of circulation. The mid-latitude cell in the middle. So we have the tropical cell, the mid-latitude cell, and the polar cell. And notice up here, just briefly, we'll have a quick look at the northern hemisphere, because that happens in the northern hemisphere, but it's a mirror image. And so here at the equator, you've got this air coming in here, and here you've got air coming up there. Now that's a head-on collision. This air at the surface is heading from the south to the equator. This air at the surface in the northern hemisphere is heading from the north to the equator, and so they hit in the middle. And therefore that causes a tendency for the air to rise because it's a head-on collision of two airstreams, and there's only one place they can go if they hit head-on, right? So it's a bit like this, right? If these two sheets of paper, if I push them together, oh, look at that. Oh, I'm going to do that again. Wasn't that fantastic? They hit and they go up. And in MET we call that convergence. They converge. That's a word most people are familiar with. Convergence. Two airstreams collide with each other and they're forced to rise. So this equatorial trough, as we call it, features very low atmospheric pressure because the air is constantly rising. And so it's given two names. It's sometimes called the equatorial trough because whenever Met men see a big area of low pressure, they call it a trough. That goes all around the whole world, those low pressure systems. But another name for it is the intertropical convergence zone. So that's a pretty flash name, but it's not that hard. Intertropical, between the tropics, the northern tropics and the southern tropics, and convergence, the air is colliding, two airstreams colliding. It's really the same thing. The equatorial trough is also the intertropical convergence zone. ITCZ, or as the Americans would say, ITCZ, the intertropical convergence zone. Now that means wherever the air is rising, the pressure on the ground will drop. And so as air goes up, it naturally releases some of the weight of the air at the surface. So low pressures are really just caused by rising air. We've more to say about that shortly. And when air is sinking, then the pressure on the ground will rise because you're standing under a waterfall of air that's coming down on top of you. And so that means that coincident with those cells, there'll be bands around the Earth of high or low pressure. There'll be a low pressure band at the equator, and there'll be a low pressure band at in here, where the air is going up. All that air is going up, so there are a series of lows. They're those mean little lows that you see on the weather map down below Australia, and you see them all the time, especially in winter. A whole string of them go across they go right around the world at that latitude, somewhere between Tasmania and the South Pole. And then wherever the air is sinking, of course, you get highs, and this is called the Subtropical Ridge. A ridge is the name that men give to a elongated area of high pressure. This one runs right around the world with high pressures. And that's because the air there sinks. And therefore it warms when it sinks. And so it's quite dry. The lows are wet because they're coming up off the ocean. But this air has already lost its moisture and it's coming down. And so across the Earth at this latitude are all the big deserts. And bad luck for Australia, we're right in the middle of it, right? Because that air that rises at the equator is sinking again in the middle of Australia. And it's no accident that all the big deserts in the world, in South Africa, and the same thing's happening in the northern hemisphere, right? Air in the northern hemisphere is rising over Africa and sinking on the Sahara Desert, which is why it's there. That's why there's a desert there, because it's constantly having sinking air producing high pressure systems. High pressure systems usually have hardly any cloud. Low pressure systems have lots of cloud. Okay, and so that is, here it is, just quickly I'll mention this before we have a break. This is an actual photograph, and of course nature's not as neat and tidy as diagrams, but you can see the effect. This band of cloud running around the Earth there they're all the lows. That's the intertropical convergence zone, or equatorial trough. And this band of these mean little lows, is usually with those big fronts coming out of them. They're very tight, low pressure systems in there, and they form south of Australia. And and here in between is the subtropical ridge. And if you look across there, you'll see that a lot of it is free of cloud. Right? There's only little bits of cloud. Whereas here you've got lots of cloud, and here you've got relatively cloud-free. And so that's called the subtropical ridge. It spends a lot of its time right over Australia, which is why we have all the droughts and constant problems with drought, because Australia's just parked in a very bad spot. And there's probably nothing we can do to stop droughts. They've always been here and there always will be, unless we can tow Australia around and put it somewhere else. Okay, let's have a break and we'll come back and go on.